Welcome to a lesson with Dr. Powell. Let's look at an example when we're computing center of mass, not just centroid, meaning that the density of the material, if this is a flat piece of material, but the density will change as we go from one side to another. Since this is not a multivariable calculus course, we'll let how this density varies depends on just one direction or one variable. So as we move this way, it'll be dependent upon x. So this particular x value, the density will be the same up and down. The density will be weight per square foot in that particular, so pounds per square foot in that particular area. So for instance, if I pick something like at what's the density right here at this moment, well, if we were to maintain this density across a whole square foot, then how much would that weigh? Well, this is the formula for how much it would weigh if we were continuing it out. So for instance, if x is a half, it would be 2 pounds in 1 square foot. So we can think of it as something like that. Okay, so how do we get center of mass in this case? This just has to do with dm, really. So before for centroid, dm is equal to dA. And how did we compute dA? This is for centroid. So at a particular x value, we have a rectangle where we have this length times our dx, and that would be area. Okay, so in this particular case, what's the height or the length of this? It would be this y value, subtract this y value at this particular x coordinate. So at a particular x coordinate, we'd have the height, which would be 4 minus x squared minus 3x of this particular rectangle. So this y value minus that y value. That's the height multiplied by dx. This is actually the dA at that particular x value. Now, what do you need to multiply to this dA value, which is area? What do you need to multiply area by to get mass? Well, in this case, it's actually force, so pounds. How do you get pounds? So how do we do that? Well, we look at this density, this force density function, and this tells us, notice this is pounds per square foot. Well, if you have square feet or area, multiply it on, you'll get pounds, right? So so you just basically multiply this on to your dA. You just take this and multiply it on. That's really all there is to it, is your dm is just not just dA, but it's dA times a function that's already given to you. That's really the only difference when you're looking at center of mass, okay, versus centroid. Very subtle little difference, but it's not really much. You can do centroids, you can work with centers of mass. So here you just multiply this on. So in making this calculation, let's compute x bar in this case. First, to compute it, remember, we need to have the area of the region. To find the area, we look at, we actually just compute, well, actually, we don't need area, we need mass, right? Because it's the total mass. Ah, yes, we need the total mass. Okay, remember that thing? So this would be the total of m, but remember we're changing what m is. So it's not just area, but it's, but this is dm, right? Aha. So how do you find the total mass? Well, to find the total mass, well, we need to add up all the little dm pieces, right? That's an integral. We add up all the little dm pieces as we go from, as m goes from 0 up to the total, and that's, you can check this is equal to m because the antiderivative is little m, then it goes from 0 to m, so it's just that. But in general, we want an integral in terms of x, right? So we got to rewrite this in terms of x and change the bounds. So actually the bounds here, they actually intersect at 1. You can check, plug in 1 here and here, you can both get 3 in both cases. So actually, if you change it to x, you're going to have an x value going from 0 to 1. And this will compute the total the total mass or the total, in this particular case, weight, but I'm using mass just because of the idea of center of mass. Okay, so be technical though, it's just weight in this case because of what pounds represent. They don't really represent mass; they represent kind of a force. Um, okay, so looking at that, we can go forward. Um, from there, what is dm? So this is dm. So we just throw this into an integral, and we evaluate from 0 to 1, and that's going to be the total area. So we need to multiply this through, be 16x minus 4x cubed minus 12x squared. And we're going to be integrating that to dx as we go from 0 to 1. Okay, so that'll be 8x squared minus 4/3. No, actually, hold on. No. Divide by 4, right? Yeah, divide by 4. So it'll just be x to the 4th. And then here, divide by 3. So it's minus 4x cubed because you divide by 3 there. Okay, and that goes from 0 to 1, which would end up just simply being 8 minus 1 minus 4, which would be 3. Convenient. Okay, so we're getting a total area of 3. So in our integration now, we're going to use this 3, take the reciprocal of it. Okay, so I have 1 over 3. Then take the integral of, now we're finding the average value of x with respect to this dm, or this m variable. So we multiply that through again. So we had, which was 16x minus 4x cubed, and then minus 12x squared dx. Okay, and we're going from 0 to 1. So now this is the integral now. So this is 16x squared, just multiplying it through, have not taken an antiderivative yet. We're just multiplying it through. 16x squared minus 4x to the 4th minus 12x cubed. Now let's take an antiderivative of this. Remembering we have the 1/3 on the outside. Okay, so we end up getting 16 thirds x cubed minus 4/5 x to the 5th minus 3x to the 4th. Okay, because we divided by 4. All right, and that goes from 0 to 1, and we're multiplying all this by 1/3. Okay, and so where this is going to compute what x bar is in this particular case. Okay, so then we end up getting 16 thirds minus 4/5 minus 3 times 1/3. All right. So let's see. And so this would be 80 minus 12. So 68 over 15. 68 over 15 minus 3, so 45. So that would be what, 63, 23 over 15 times, so it'd be 23 over 15 times 3, oh, 1/3, so 23 over 15, so 23 over 45. Okay, so 23 over 45 would be equal to x bar in this particular case. Yeah, I'm just making sure that was right here. So 68 minus 45. Yeah, I'm pretty sure that's right. Okay, so 23 over 45 would be x bar, and does that make sense in the sense here? This case, so 23 over 45 is about like, it's nearly half-ish. Yeah, it's just slightly more than half. Does that make sense in the calculation? Um, Maybe so. It's kind of hard for me to. I was thinking to be a little bit more over there, but nonetheless, we just computed x bar and a little illustration of what you do when it's not just centroid. Oh, maybe that's why. Aha, because there is a little bit of weighting. I see. Because even though there's less area over here, so maybe this might not be the centroid. So we can't use the centroid intuition. But over here, what do we have instead? We have the mass is getting greater, even though the area is getting less. And so, or the force rather. And so it's kind of counterbalancing itself out, and it counterbalances itself in such a way that it actually pulls this just slightly to the right of halfway. Um, let's see, 20, yeah, slightly more than halfway across in this direction. Thanks for watching.